Happening in year 12, this is section 12.9. It's on something called stationary points. So stationary point is a point on the graph where the gradient is flat or the gradient is 0. Okay. Now, if you remember right the way back to when we first started talking about differentiation, and I put a diagram on the board, it was a little bit like this, and imagined you to picture sort of trying to climb over it or trying to get from here sort of across up to there. And we talked about these points where the graph effectively either topped out and started to come back down or bottomed out and started to go back up. They are the stationary points. Okay, this one is a maximum, a local maximum. Ignore the word local, I'll explain that one when we're sort of together again. And B is a local minimum. Okay, so that one maxes out up there. This one bottoms out, minimizes out, if you call it, down there, and that one goes up. Okay, so at those points, the gradient is 0. So to find a stationary point, we differentiate and then set it equal to 0. Okay, so that's the main thing that you're going to be doing. You're going to set dy by dx equal to 0, or if they give you it in terms of f of x, f dash equals 0. That will then give you x at the stationary points. Okay, so obviously then if they want the coordinates of the stationary point, you then sub your value of x back into the original function to get your coordinate for x and y. Okay, now there is another type of stationary point called a point of inflection. Now if you notice there in the middle, that point O, that is flat there. Okay, the gradient there will be flat, so the tangent there will be flat going across that way. The tangent here at B will be flat, so it makes them two stationary points. The tangent there at the point at the origin is flat as well. However, it's not a minimum or a maximum. It's what we call a point of inflection. It's where it just goes horizontal for a second, but then continues to drop after it. Okay. Now, they are harder to spot because one of our little kind of tests for whether it's a maximum or a minimum doesn't actually work on it. What happens is you end up having to kind of test it yourself a little bit. Now, let's just consider this point up here. Okay. Imagine, look at the gradient coming up to the point A. So if you were down here, the gradient there is almost vertical, which means the gradient is really, really steep at that point. If you imagine being down at that point, it's there. Now, as we move along the curve, the gradient still stays positive, but it starts to decrease. Can you see the way the pencil is becoming a shallower angle, shallower angle, shallower angle? That means that the gradient is decreasing each time, okay? Until we get to the point at A, where the gradient is 0 there. Okay, so as it's coming up to here, the gradient, the steepness of this curve is decreasing, and then as it goes after that, it continues to decrease, going more and more negative the other way. So what that means is that the change in the gradient, if the change in the gradient is negative or less than 0, then it's a maximum. That's what that is there. Okay, remember that means your second order derivative. If the second order derivative is negative, it means that it must have been a maximum, because it means that your graph must have topped out at that point. It means that the gradient must have been very, very steep moving up to it and then getting less and less and less steep to the point of your local maximum, and then it's getting decreasing afterwards like that. Okay, and vice versa. Imagine being sort of here, there it's really kind of steep negative wise. If we do the same sort of thing with the pencil, really, really steep negative wise around about there, and then it is getting more and more shallow, but still staying negative, more and more shallow, still staying negative, until it hits B, at which point it's 0, and then it starts to increase and be positive again until it gets quite steep, sort of up to there. So when d2y by dx squared, your second order derivative, is positive like it is there, that gradient, as we move from, say, this point here to this point here, is actually increasing. It's negative there, but getting less and less and less negative up to 0, and then it's getting positive. So if it's gone from being negative to being positive, it means that it's increasing, which means d2y by dx squared is positive, which means that that must have bottomed out between there and there. So that is a minimum point. Okay. Now, the points of inflection, if we consider that before it there, the gradient is negative, isn't it? And after it, it's still negative. So if you end up with your second order derivative equaling 0, it means that it's a point of inflection, which means that the gradient doesn't change in terms of positive or negative from one side to the other. You just have to test that yourself. You'll see what I mean in a second. Okay, so the two key things that we're going to be doing today are differentiate, set it equal to 0 to figure out where our stationary point is, and then using our second order derivatives to see whether it is a maximum or a minimum. And if the second order derivative is negative, it's a maximum. If the second order derivative is positive, it's a minimum. Okay, those are the two key points about what we're going to be doing today. So over here for example 16, find the coordinates of the stationary point on the curve with equation y equals x to the 4 minus 32x. Okay, and then part B, by considering points on either side of the stationary point, determine whether it's a maximum or minimum or point of inflection. I'll come to that part in a second. So whenever you see something like this, find the coordinates of a stationary point. They could also say there either maximum point or minimum point. And you have to kind of spot that that means a stationary point. But if you want to find the coordinates of a stationary point, we get dy by dx and we set it equal to 0. So that's what we're going to do for part A. So if y was x to the 4 minus 32x, dy by dx, you should now all be kind of chanting to yourselves over and over again in your head, times by the power decrease the power by 1, times by the power decrease the power by 1, times by the power decrease the power by 1, and we do that to both of these terms. Times by the power decrease the power by 1, it's going to be 4x cubed, and remember when we just got an x to the 1 effectively there, times it by 1, that stays 32, decrease the power to 0, x to the 0 disappears. So that is our derivative there, that's our differential, our gradient function. Because it's a stationary point, it means that we know that this must equal 0, so we now set it equal to 0. We've now got an equation to solve. When we solve this equation, it will tell me what x equals at the stationary point. Okay, so the way I'd solve this is divide everything by 4 and then bring the 32 over to the other side. So I'm going to get, sorry, I'm going to divide that by 4, it's going to give me 8, isn't it? 0 equals x cubed minus 8, which means that 8 equals x cubed, which means that x equals 2. Okay. Now, it asked me for the coordinates. I've only got my value for x. How do I get y? Because at the minute, what I know is that my coordinate looks like this, but I need that number there, which is y. So I need to use this in the relationship between x and y. That means I need to sub it into something, which means I need to sub it in to this here. Okay. If you remember, we spoke about that last time about what to sub it into. We want the y coordinate, which means that we sub it into the thing that begins with a y. So y will equal 2 to the power 4 minus 34 times 2. And if you plug that into your calculator, you're going to get there 2 to the power 4 minus 32 times 2, which gives me minus 48. Which means that my stationary point occurs at the coordinate 2 minus 48. Okay. Right, part B then. By considering points on either side of the stationary point, determine whether it's a local maximum, a local minimum, or a point of inflection. So we know that the stationary point happens at 2 minus 48. So consider that. That's when x equals 2. So let's consider when x equals 1, what's happening to the gradient, and when x equals 3, what's happening to the gradient. Okay. Now the gradient is this thing, remember. So when x is 1, we're going to get 4 times 1 cubed minus 32, which is going to give me minus 28. Okay. When x is 3, the gradient will be 4 times 3 cubed minus 32. I'm going to put that into your calculator, can't do it in here. 3 cubed minus 32, which equals 76. Okay, so this one is negative, this one is positive. We've gone from negative to, we've gone from negative to positive, which means that the gradient must have gone from coming down this way to now being going up that way. So it must have been a minimum point. Okay, so because we went from a negative point to the left of it to a positive gradient, so negative gradient on the left of it to a positive gradient on the right of it, it means that it must have gone from coming down that way to going up that way, which means it must have bottomed out, which means it must have been a minimum. Okay, right, example 17, part A, very, very similar. Okay, so if you think you can do this one on your own, just stop the video, have a go at it yourself, and then come back and check, but it's effectively the same type of question as part A on example 16. So find the coordinates, the stationary points of the curve with this equation. So we're going to do dy by dx and then set it equal to 0. So that's going to give me 6x squared minus 30x plus 24. And I want to set that equal to 0 because it's a stationary point. Okay, and then remember, that is a quadratic. Just use your calculator to solve it. Do not waste time if you don't need to. Factorizing and all that kind of stuff. So there we go, plug them into the calculator. 6x squared minus 30x plus 24. So we'll get answers there 4 and 1. Okay, and then I need to figure out, because again it wants coordinates, doesn't it? So I need to figure out what y is for each of them. So plug them back into this. So when you plug 4 into there, I think you end up with something like minus 154. When you plug 1 into there, you end up with 17. So our stationary points are 4, minus 154, and 1, 17. Okay. So part B, find the second order derivative and use it to determine the nature of these stationary points. So we've got dy by dx there. We can figure out what our second order derivative is here. The times by the power decrease the power by 1 again, so that's going to be 12x minus 30, and then use it to determine the nature of the stationary points. So this is the main way that we figure out whether it's a minimum or a maximum. We're going to sub x from each of these coordinates into this. So 12 times 4 minus 30, so it's going to be 48 minus 30, which is 18, which is positive. So therefore, if it's positive, it means that it must have been a minimum. Okay. Remember, what that means is that the gradient is increasing. That's what that is. So it means that it's gone from being negative to being positive. So if the change in the gradient is positive, it means that it must have bottomed out at a minimum. And let's do the same thing for this one. We're going to get 12 times 1 minus 30, which is going to give me minus 18. Which is negative, which means that it must have gone from being positive to being negative. So it must have gone from being positive that way to being negative that way, which means that that one must have been a maximum point. Okay, so this one, when it's positive, remember it means the gradient's gone from being negative to being positive. It's changing in a positive direction, so it's a minimum point. This one, it's gone from being positive to being negative, because the change is negative, so it's a maximum point. Okay, if you don't fully understand the actual kind of sort of logistics and logic behind that, just remember that it's the kind of opposite way around that you'd imagine. If that is positive, it's minimum. If that is negative, it's maximum. Okay. And the last example over the page, we've got example 18. So the curve of the equation y equals 1 over x plus 27x cubed as a stationary point at x equals plus or minus a, find the value of a. Effectively, all this is asking us to do is figure out what value of x occurs at this stationary point. Now the difficulty here, well, it's not particularly a difficulty, it's just this term, isn't it? We cannot differentiate that at the minute, so we need to write that as y equals x to the minus 1 plus 27x cubed, and then the rest of this is exactly the same as what we've done on the other questions. Figure out where the stationary point is. So figure out dy by dx times by the power, decrease the power by 1. So times that by a power, will turn it negative. Decrease the power by 1 will go to minus 2. Do the same thing with this, times by the power, that will turn that into 81. Decrease the power by 1, that will turn that into 81x squared. Now because it's a stationary point, we set it equal to 0. And what I'm going to do is I'm going to turn this back into a fraction. The reason I've done that is because now that we're solving an equation, I don't really want to deal with negative fractions because it's easier to deal with things being on, negative indices, because it's easier to deal with things when they look like this when we're solving it. It's easy to deal with them when they look like that and we're differentiating it because we must have a power. But when we're going to solve an equation, we don't really want to deal with negative powers. We prefer to deal with things on the bottom of fractions because then we can cancel fractions and all that kind of stuff. So to solve this, I'm going to bring this term over to this side. So I'm going to get 1 over x squared will equal 81x squared. I'm going to times both sides by x squared to get rid of this fraction. So I'm going to get that 1 equals 81x to the power 4. Divide by 81. And then do the 4th root of 1 over 81. Now, if you don't know what that is, hopefully some of you just know that that's 3. But if you didn't, what you would have to do here is there is a button there in gold that allows you to put in what root you want. So you want the 4th root of this thing. So do 4 and then put in your 1 over 81 in there. Okay, that'll give you the 3rd. And just remember that that is plus or minus a 3rd. Okay, so that's what a equals there. Right, so what I'd like you to do is on the next page, I just want you to do the highlighted questions there. Okay, question 1 and question 2 are asking you to figure out least values for curves and greatest values for curves, and they're all quadratic curves. So effectively what this is asking you to do is to figure out the minimum point on that curve and the maximum point on that curve. Now we've done that by completing the square before. You can do it this way as well, but we've already done that by completing the square. So I don't think there's any point in doing question 1 or question 2. Question 3, 5, 6 and 7 are the ones that I'd like to concentrate on, and I want you to do at least, you can do more of these if you want to, but 3, A, C, E and G. Question 5, question 6 and question 7. Okay, so what on these ones, find the coordinates of the points where the gradient is 0, and then establish where the maximums, minimums, or points of inflection. So get dy by dx, set it equal to 0, then get your second order derivative. Sorry, get dy by dx, set it equal to 0 to get x, sub that in to this thing to get y, to get your coordinates, then get your second order derivative, sub in x again. If it's positive, it's a minimum. If it's negative, it's a maximum. If it's 0, it's a point of inflection. Okay, so do that for this one, this one, this one, and this one. With this one, be careful with this thing. Remember that's going to be x to the minus 1. And remember that is going to be 3x to the half. Be careful there. Okay, this one, by considering the gradients on either side of the stationary points on the curve. This, show that it's a point of inflection. And then sketch the curve. So get dy by dx, set it equal to 0 and solve it. You don't really on this one need to figure out y at that point. Once you've got your gradient, once you've got your x value for the stationary point, sub in a number below that to this thing and sub in a number just above that to the to your gradient function again, and you should see that they're either both positive or both negative, so therefore it's a point of inflection. This one, find the maximum value and hence the range of values for the function this thing. Okay, so your maximum value, basically just figure out the stationary points and then from there have a little think about what values that's going to give you. Okay, because if you've got a maximum value, it means that your curve can take any value up to that point. Okay, that is your range. And then for this one, find the coordinates of the stationary point and determine the nature of each. Now the problem with this is that when you differentiate it, you're going to get a cubic, which means, as this little hint over here talks through, you're going to have to use the factor theorem to figure out values for that, and then you're going to have to solve a cubic basically. So use the factor theorem, so sub in numbers. So if you sub in 3 and it gives you 0, then that means that x minus 3 is a factor. You're then going to have to do your long division and factorise what you get left, and that will give you your 3 linear factors, which means that will give you your 3 values of x for the 3 turning points on that graph. Okay, so have a go at those, please. You can use the solution bank to help you, and then can you upload a picture onto Classrooms of the work, please, so that we can see that you're doing it. Okay, any issues, just drop us an email and I'll try and get back to you as quickly as possible. And remember that we need this done by Sunday. Okay, nice one. Good luck.